So my name's Chris Russell. I'm a research fellow here at the Institute, so I'm in every day, but I'm also associated with the University of Edinburgh. Sorry, my voice is going. I'm primarily an optimisation guy. So this means I jump around a lot from topic to topic. So a bunch of things I've worked on which I don't have time to talk about today, but you might want to grab me later, include segmentation and particularly fusing together different cues in order to make sense of what's going on in the world. So combining depth and sort of like object class labeling, knowing that something is a road and therefore it is a certain distance from the camera, lies in the ground plane. Fusing like object detectors with segmentation again, recognizing something is a person and therefore you can label pixels in that region of the image as being a person as well. And using things like semantic knowledge of how labels fit together in order to make sensible hypotheses of the world, sort of like simple descriptions which make sense and tell you what's going on. And a lot of learning, sort of like the more eclectic kinds of learning. So weakly supervised learning, unsupervised learning for object detection, manifold learning, and forget what that's called. Anyway. And also understanding social grouping. So given images, videos of people talking, how can we work out what the conversational groups are, who's talking to who, and what's going on. What I'm actually going to talk about is, building 3D models from a 2D video. So given a simple video as an input, what we want to be able to do is extract a moving dynamic world which gave rise to the video and figure out what's going on in 3D. And the question is, why think in 3D? Well, as soon as you start using robots, as soon as you want to start actually talking about what is going on in the world, you need to have this like 3D model of where everything is so you know how to interact it, how to stop this kind of thing from happening. And why are we doing this with video? And the reason is video is everywhere. We've got archive footage, we've got the whole of YouTube. There's more footage than anyone has time to watch. We have old films, we have things captured on phones. We have things like keyhole surgery, where you cut a tiny hole in someone, you poke down a very small camera, and you don't have enough space to get down big capture equipment, so you can actually find stuff in 3D. You can only look in 2D. And it's reliable. It works outside, which, unlike the Microsoft Kinect. It works on moving objects, unlike structure from motion. It works from a distance, unlike basically everything. And it works in low-powered environments. Cameras are cheap, and they're easy to use. But it's also a really hard problem. So it's mathematically ill-posed because every time we take a picture of the world, we destroy information. We move from 2D to 3D, and the fact that the world is changing all the time, things are moving, means we can't just take a bunch of different pictures and use each picture to destroy slightly different information and then fuse it together. We have to do something else. We have to cheat. Okay, and this is one of my earlier attempts at cheating. And the idea here was that given a video we've literally just taken off YouTube, how can we reach out, segment it, split the video up into different objects, and then reconstruct each object in 3D. Right. So the way this is going to work is we are going to split each object up into sort of a proto-skeleton, if you like, a bunch of almost rigid parts which correspond to like essentially bones of the object or large, nearly rigid parts which are moving around. And each object is going to be a bunch of these parts stuck together. So in this case, you see the whole of the world behind the bike is a rigid piece. The guy is jumping on the bike, and as he jumps on the bike flexes. So you have two parts of the bike. You have the top half, and then you have a back articulated wheel. We don't really recover the whole skeleton of the person because this is very lossy footage and there's not enough detail to see what's going on. But we still split them into two parts, the part mostly associated with the bike and then the rigid sort of like top, head and shoulders of the person. And this is good enough to get back a 3D reconstruction. So, I mean, the reason we do this and the reason we split things up into these rigid parts is that normally when you're doing non-rigid reconstruction, you like the camera to move really fast around the object. So you get lots and lots of information, and then the idea is that the new information coming in dominates the deformations of the object. You can treat it like it's almost rigid. That doesn't work in the real world, where you can't have a camera rotating around someone at 100 hertz a second. So what you do instead is you say, well, if I treat it as piecewise rigid, then every time something moves, like its pieces rotate and twist. And this actually gives us the 3D knowledge about the world we can then use to reconstruct each piece. So the way we do this is we go through, we start off with like hundreds of candidate models, and we fit each one of these to like little local regions, and then we throw away ones which aren't making sense, which we don't need. We use this to come up with an overall labeling of what's going on. We refine this, then we refit the models, and we just keep bouncing back and forth until you get something that works. And one of the catches here is you need neighbouring parts to overlap. And this requires a whole new kind of segmentation which didn't exist before. The reason you need this is because if you're doing piecewise rigid reconstruction, each piece has this scale ambiguity. You don't know if something is small and very close to the camera or very, very big and far away. By making the parts overlap, we can say, well, the points they both models predict must be consistent, they must agree, and we can use it to pull everything together and get back decent reconstructions. And this works quite well on very nice clean data, captured in a mocap studio, and you can get back decent 3D reconstructions of what's going on. The challenge we had was like, okay, well, let's take it into the real world and see what happens. And in order to do this, you go, well, I just said there's a bunch of pieces. I didn't really assume there's only one object in the world. So all I need is that parts from different objects don't overlap. And then I can handle multiple objects moving about in the world, and I can treat the whole world as itself as another object with like dynamic actors wandering around in it. Right, so this requires, whole new segmentation model. So what we do is we have this assignment cost of like having a motion model applied to a point, and we subject this to overlap constraints. We say, okay, well, if I say a point belongs to the blue model, it must also pull in its neighbours in some kind of neighbourhood graph and force them to belong to it as well. Which was challenging. I'm going to skip over costs because we really don't have time. And so that was the previous formulation. And onto this, we added an edge drop cost, which says, okay, when we're building this graph, it often goes wrong because we don't know the 3D world when we're doing it. We just have some kind of tracks which aren't quite right. So we want to be able to discard edges in this graph and go, oh, actually, these two pieces shouldn't be overlap. We also want an overlap sparsity term, which says generally pieces shouldn't overlap, and we want something driving it towards this very compact, cohesive formulation. And we have another term which says there should be as few terms as possible. So this was the new difficult to optimization part of this paper. That one there took me most of my PhD, and that one there was the first paper I did as a postdoc. So it was a lot of papers just to get this thing working. So why do we need this graph breaking, and why do we need to delete stuff? Right. Okay, so here we can see what happens without graph breaking. You get back coherent sort of parts. Everything makes sense and they work as like a skeleton of something. But when you come to look at the objects themselves, the video is not working. And the mouse isn't working. Okay, you're going to have to take my word for it. Everything comes out as a single object, and it's all tied together because the tracks haven't worked. As the object moves, it drags things along with it, and you get this sort of ambiguous kind of flowing together of everything. So if we drop edges which cause inconsistent models to overlap, and we use this sparsity prior to drop small regions of overlap, if there's only a couple of points overlapping, it's probably a false positive. Then suddenly everything works, and now we get back people as single objects, we get back tractors as single objects, and a bag. So it's all good, it all works. You then go, well, what happens if the world is a bit ambiguous and there's not enough motion information going on and we can't really see enough to work out what the parts are exactly? So an example is this, and if you pay attention to that foot there, as it moves, it does slide along the floor. It should be a separate thing to the floor, but because of the way the camera moves, as the person does, it's actually consistent with just a rigid part off in the distance, sort of swinging with the camera. And once you make this kind of mistake and you lock the foot to the floor, you can't recover from this by just deleting edges. It's like, no, it's a single coherent part. So when we're making this kind of decision, what we need to do is use more information, obviously. And what we did is we used a previous work we'd done on detecting objects in an unsupervised way. I mean, essentially, it's very hard to say what is an object compared to, because they all look different in their own way. But what we found is that the world is very repetitive, it's very similar, so you can just discover objects by building a model of the background, essentially, and saying what is not background. And this is a nice, cheap way to find objects. So we do this, we apply this, you get something like this as a unary cost, and you're just saying like, okay, well, each part should have fairly consistent appearance. It should be as distant from the background as any other part. Great, and that works, and this is the sort of thing that, God, what has happened to those videos? All right, okay, this then gives you back decent 3D reconstructions and proper parts, so we can then split everything up. Standard, yep, it works on vision data sets, great. Yeah, and here are a few videos where just sort of showing stuff where it works. So for me, like one of the most interesting things about 3D reconstruction is the idea that really we should be cheating, and we should be using as much knowledge about our world as we have to inform our reconstructions, which can then feed back in, and we can then start using our better reconstructions to get better knowledge about the world. So, right. One of the things I was interested in is how can we use sort of like knowledge of how the world fits together physically, that blocks have to hold up other blocks, in order to get better 3D reconstructions, models that you can actually interact with, sort of like slam around in a physics simulator or tell robots how to pick up a block and knock things over. So we can go from like having 4 very badly matched silhouettes like this to a physically plausible model of the world where we can say, okay, well, it's a temple. How would it fall to pieces in an earthquake? And you can start shaking stuff, and is that coming out? Yeah, kind of. And we can get back decent 3D reconstructions, which you can really interact with. You can put into physics sims and use for movies and stuff. So the reason for doing this is, as well, because structures and semantics interact, right? If you look at this model of a car, you immediately know how is it going to move, how you can actually push it along the world, how it will turn, and these kind of things. And we really should be exploiting this in reasoning about how the world fits together and what's going on. And also, it's a great excuse to play with Lego, which, yeah, I think is, yeah. So, okay, we go through. We start off, we've got a bunch of images, we extract silhouettes, okay, and now we need to find a physical model of the world which has this kind of structure and tells us that the world fits together in this kind of way. These videos are really not working. Okay, so you go, oh, okay, well, that's fine, right? I just stack together all my blocks, I project them into 2D, and I look at the silhouette, and I say, well, how are they different? So, oh, okay, well, that's easy. I can just do this, and I can write it down and solve it. And, of course, the reason I'm telling you this is because it doesn't work at all. And what goes wrong is, well, okay, when I've got the silhouette is either 0 or 1. When it's 1, I really want there to be a block there. But sometimes there's a bunch of blocks along that ray. And when I project them, they all add up, and you get a number much bigger than 1. And suddenly, when you try and solve this, everything gets driven towards fractional solutions, and you end up with half bricks everywhere. And it's horrible and useless. So instead we go, okay, well, how can we solve this? And we go, well, bits inside the silhouette are easy. Outside the silhouette are easy. We know there definitely shouldn't be a brick there. So if one turns up in the silhouette, something's gone wrong, and you'll pay a cost. Inside the silhouette, well, what we actually know is there's at least 1 brick there. And you can write this down as a linear constraint, and every time you violate it, you pay a cost, which is fine. And Okay, good, it's working. Because we're dealing with really big bricks, like normally when you're doing 3D reconstruction, you deal with voxels, and they all have unique 3D locations, so they can't interact with each other. But when you're dealing with big semantic parts that can support each other, suddenly they can intersect. And this is really bad. It's not physically plausible and doesn't tell you anything about the world. So what we say is that at any voxel, only one part present in it is turned on. Again, this is a nice linear constraint, which is leading us towards like this is not too bad to optimize. And we also need something like the model must be physically plausible, right? If nothing is just floating in the air. So if a block is turned on, then one of the ones below it must also be turned on. Again, yeah, great, linear constraint, good, getting there. This is all feeling like it's kind of optimizable. But do we need this constraint? Is a reasonable question. Can you see what's going on at all? God. Right. Is that playing? No. Okay, so it's interesting. You think, like, okay, I have a physically consistent world, and I'm making a reconstruction which looks like it anyway. So shouldn't it stand itself up? Because that's what physics says. And it turns out the answer is no. It's really important to explicitly code this. And the reason it's important to code it is that as you get towards the bottom of the image, or the bottom of the object, you can't see much. It's like it starts occluding itself. And you end up with these holes and stuff in space where you don't really know what's going on. And without physical constraints saying it must be self-supporting, the whole thing just topples over. So results, this works, and don't know, I spent ages on these videos and they just don't work. So yeah, it's great. We can now take pictures and we can just say, okay, well, how would a wrecking ball interact with this in the world? And we can get, if not the right answer, we can get a very plausible guess, which is telling us something about what's going on in the structure of the world. So we can also say, how could I build anything you like out of Lego? So this is a classic vision data set for years, and people have been like coming up with different reconstructions of this toy dinosaur. And I think this is the first Lego one. And it's physically plausible, and we can actually build this, which is quite nice. And of course, yep, this is the Eiffel Tower as done by a 4-year-old child or a lot of computing processing. Yep, and so, yeah, works nicely on, yeah, these big brick-like structures as well. And something just want to cover as well quickly is, like, suppose we had a bit more knowledge about the world. Suppose we knew what we were trying to reconstruct was a face. We had a decent model of like how someone looks at one point in time. Could we then use this to go through sort of like and build a much better sort of like lifelike and vivid reconstruction of a person? So in this case, what we do is we just grab a camera and we say hold still. We move the camera around someone and we use this to build an initial 3D model of the person. Given that 3D model, which yeah, you can then sort of like start saying, okay, well now I'm going to take the model and I'm going to warp it so that in each frame it looks something like the image. And this is a photometric consistency term. It's like, okay, match the eye of the dog to the eye in the picture, and we bend it in such a way that it deforms as little as possible. And there's two types of regularizer which are commonly used for this. One's called as rigid as possible, which is essentially this rubber mesh model where you sort of preserve local rigidity but allow stuff to bend. And the other is the standard regularizer, which just snaps it back towards the template. So, I mean, essentially what we're doing here is we're tracking. PowerPoint has crashed. This is a Scooby-Doo model. We build a big rubber mask of someone's face, and then we stretch it and we deform it to show what's going on. And so, yep, it's great, it works, good. And there's no assumptions about faces really, we just need something and we can start tracking it, we can see what's going on, and we can generate 3D flows showing like how each finger is moving individually and this kind of thing. So it's all kind of cool. And then you go, okay, great, now it's time to take this out the lab and let's see what actually goes wrong and like how does it work in the real world. One of the problems we have is artifacts coming from the fact that we're using Hooke's law. And I like to think of these as like Coke can type artifacts. When you take a Coke can and you crush it, it bends in such a way that it doesn't stretch at all, because steel is, although it's an elastic material, it hates stretching. So you get these like crumpling and buckling artifacts where everything is, locally it's stayed rigid-ish, but it's got these horrible deformations and spikes in. And in some of our reconstructions, you can see these kind of weird artifacts around the head of the dog when the deformations get too strong and take over. And the model doesn't quite know what's going on or how to deal with stuff. So you go, okay, well, all right, the first thing to do is that, can we fix this? Can we build a better physical model of what's going on? If we have better knowledge of the world, if we use wider regions, sort of like make it more elastic and pull in large areas, can we stabilize it a bit more? Can we use smoother deformations? Or there's been a lot of work recently on volume preservation, where you go, okay, well, it shouldn't change, it shouldn't buckle inwards, basically, and by preserving volume, we can stop this from happening. Turns out better data is a much easier answer and saves us actually having to code any of this stuff. So one of the problems we have here is that even if you're working on a synthetic sequence where you've got no specularities, you don't have very hard shadows, as people move, as they talk, the lighting changes as it falls on your face. And this changes the color of what you're looking at. Because the color of someone's face is a mixture of the, yeah, we get tracking failure. Because the color of someone's face is a mixture of the intrinsic color of their skin and lighting artifacts. So as you go out into the real world, you suddenly move away from these nice sort of like bright, uniformly lit spaces, and you start getting shadows, point lights, and everything goes wrong. So all we need to do to get rid of these artifacts is to actually describe what's going on. So we say, okay, someone's face is a mixture of some kind of intrinsic color multiplied through by shadows, which are a function of how the surface normals of the face point away from light sources, and some shiny specularities. So yeah, the intensity is the albedo multiplied by the diffuse shading, which is, yeah, normals, illumination, and then specular highlights. Good, so, yeah, this works surprisingly well. It's like this was actually the missing ingredient in what's going on. So suddenly tracking is now nice and reliable, and what's even better is because we need good surface normals to track, we get for free much better detail about what's going on. Suddenly the little creases about the eyes and the mouth, which tell you if someone is genuinely happy, if they're actually enjoying what's going on, what they're thinking, what they're feeling, these semantically important details start coming through, and suddenly this is cool. This is something you could maybe use in a movie at some point. And also it lets us deal with sweaty people and shiny surfaces and this kind of thing where if you have a light shining on someone and it moves, you get this glossy reflectance back. But it turns out it's really important to capture this. If we don't capture it at all, the whole lighting model fails and everything goes wrong uniformly across the image. But if we do capture it, then yeah, we get back nice, reliable reconstructions. And of course, nothing actually depended on this being a face at all. So it works for generic objects as well.